In this video, we're going to go through generating irreducible representations for the sigma bonds in water. So we went over this in class very briefly, but there were some questions after class, and I thought it would be best to actually go through and then show how to generate the reducible representation and then pull out the irreducible representations from that, and then finally generate the MO diagram. So if we look right here, we have two sigma bonds. So we have one between that oxygen and hydrogen, and then we have another one between the other oxygen and hydrogen. Oh, apologies. It should be sigma 2. And so if we go through this right now, we can see what happens in each one of these cases. And so if we start generating the reducible representation right here, so it'll be the two sigmas, we can see that in the case of the identity, both sigma bonds remain intact, so we get a value of 2. If we rotate the molecule by the C2 axis, which is located right here, and that rotates this hydrogen into this hydrogen right here, we can see that the sigma 1 becomes the sigma 2, and the sigma 2 becomes the sigma 1. So both of them move, and so we end up with a value of 0 in that case. The next symmetry operation is the vertical sigma v in the xz plane. And so I'll say that the oxygen and the hydrogens are going to lie on the xz plane, and so we will have our sigma v xz right here. And so in that case, both sigma 1 and sigma 2, both of these bonds are going to remain in place, and so we'll get a value of 2 in that case. And so now we will also then have the sigma v in the yz direction, which is going to then turn this hydrogen into this hydrogen and so forth. Same thing will happen with this sigma 1 is going to turn into the sigma 2 bond, and so we will then get a value of 0. And so for water, our reducible representation for the sigma bonds is going to be 2, 0, 2, 0. Now to break that down, we're going to want to use the formula that we discussed in class. And so if we apply it to the A1, what we can then see is that we have an order of 4. We have 4 symmetry operations total, and they don't have any numbers before them, and so we end up with a value of 4 for the order. And so then in the first group, we can see that there's no number in front of the E, so we have a 1 times, in this case, we will have the character is equal to 1, and then we will multiply it by the character of the reducible representation, which is 2. The next step is to then look at the C2. The C2 does not have a number before it, so it'll be 1 times the character of the C2. In the case of A1 is going to be equal to 1, and then we will multiply that then by 0. Next, the sigma v xz does not have a number before it, so it'll be 1 times the character, which is 1, times the character of the reducible representation, which is 2, and then finally we will have our sigma v in the yz direction, which will then be 1 times 0 right here. And so if we add all of this up, we can see that we then have 2 plus 0 plus 2 plus 0, which gives us a value of 4. We divide that by the order, we then get a value of 1. So we know that one symmetry adapted linear combination is going to have an irreducible representation of A1. Now if we go to the next one, the A2, what we can then see is that as we work our way through it again, and I'm going to be working through it a little bit faster this time, we can see that E is still positive, it's still equal to 1. We can see then it doesn't matter for this one right here, right? Because no matter what, we'll end up with 0 because the reducible representation has 0 right there. The next step will then be looking at what happens in the case of the sigma v xz, and so in that case, when we multiply it, we will then change the character of the sigma v from 1 to -1, and when we multiply that by 2, we will see then that this becomes -2, this is 2, and then right here we just add 0 again because we have a value of 0 for the reducible representation, and so 2 minus 2 is equal to 0. So the reducible representation does not contain the H2 character. And so if we work our then way through the next portion, so the B1, we can then do all of this again, and we can see that B1 has a value of 1 for E, and so then that should remain 2. We'll then have plus 0, again because of the reducible representation having a 0 right there. The sigma v xc will have a value of, has a character of 1 for the B1 representation, and so then 1 times 1 times 2 will give us 2 in that case, and then we have 0 again, and so we will end up with 4 in here, and then divide that by 4, and we end up with 1. And so then we can see that the sigma bonds symmetry adapted linear combination also has B1 character. Now, we can easily see that we don't necessarily need to go on to get B2 because we can already figure out that this is actually all of the irreducible representations present within this reducible representation. And the way that we can see that is if we add up A1 and B1, we'll end up forming the reducible representation. So if we take 1 plus 1, we'll get 2. 1 plus minus 1 gives us 0. 1 plus 1 gives us 2. And 1 plus minus 1 gives us 0. And so we can see right here that we have our reducible representation by adding those two up. If we were to have the B2 as well, that would be present, what we would then get is 1 plus 1 plus 1, so we would have to have a value of 3 right here. For in the case of the C2, we would have to then have a value of minus 1. In the case of the sigma v xc, we would have to have a value of 1, and in the case of the sigma v, we would then also have to have a value of 1. But because we don't have that, we can see that we only have B1 and A1 symmetry. So these are the symmetries of the symmetry adapted linear combination of the SALCs. And so in a second, we'll then go through and generate a molecular orbital diagram utilizing our SALCs that we just generated and combining them together with the orbitals of the oxygen to form the MO diagram for this species. So now that we have generated the symmetry adapted linear combinations for the sigma bonds, we can now start generating the molecular orbital diagram of H2O. And so to do that, you can see that right here on the right, I have the 2 hydrogen atoms, and they're 1s orbitals. And so those orbitals will have then A1 and B1 symmetry. And so the way that those will then look in the case of the A1 is that they will both be of the same phase, whereas in the case, let me just label that real quick for you guys. So that's the A1. And then in the case of the B1 is that the 2 of them will then be out of phase. And so both of these will generate sigma bonds with atomic orbitals on the oxygen, but they will not necessarily be of the same energy. As we've previously stated, there's the 3 rules to be able to generate molecular orbitals. The first one is that the atoms that have those orbitals have to be within close enough proximity to actually form bonds. The second rule is that you want to be within approximately 15 electron volts. The 2s orbital on the oxygen is much lower than the 1s orbitals of the hydrogen atoms that are forming these bonds, and so the overlap won't be that great, and it'll result in very minor stabilization of the molecular orbital that can be formed between the hydrogen and the oxygen 2s orbital. There'll be much better overlap between the 1s orbitals on the hydrogen with the 2pz orbitals and the 2px orbital on the oxygen. Now, the third rule is that we have to have the right symmetries. And so I kind of just alluded to that just now in that we have one linear combination that has A1 symmetry, and we have another linear combination that has B1 symmetry. And so in the case of the A1 symmetry, you can form molecular orbitals between the 2s, which also has A1, as well as the 2p, which has A1 as well. And so you can see that by looking at the character table for C2v and seeing that in the linear column that we have the z coordinates have A1 symmetry, and then in the quadratic column that the x squared, y squared, and z squared coordinates have A1 symmetry as well. In all cases, the 2s or any s orbital will always have the totally symmetric symmetry. It'll always be A1 or a derivative thereof, as it's a sphere and completely symmetric all around. However, in the cases of the 2pz, that'll not necessarily be the case. It'll change from point group to point group. And so we can then also assign that the px orbital has B1 symmetry, and that the py orbital has B2 symmetry. And we can get all of that by just looking at the character table. And so by doing that now, we can see that we should be able to generate the MO diagram. And since we're putting in 3 A1 orbitals, we should get out 3 A1 orbitals within our MO diagram. And so we'll end up with one A1 that'll be down here, and it'll be very close in energy to the initial 2s orbital that we have present. The next orbital will be the 2A1, which will be located right here below the 1s orbital. So let me just start drawing these connections. And then finally, we'll end up with the 3A1 up here. And that's going to then be the primarily anti-bonding orbital overall. And so the 1A1 will have some 2pz character, and the 3A1 will have some 2s character to it as well, but it'll be very minimal in comparison to the other orbitals that will be present in those cases. Now, the next orbitals that have the correct symmetry will be the B1 combination of the hydrogen orbitals and the px orbital on the oxygen. And so in that case, we can see that we'll then end up with a 1b1 orbital down here, and then another b1 orbital up here. And so finally, the only orbital that's left that doesn't have a molecular orbital for it would be the py orbital. And the py orbital has B2 symmetry, so it doesn't have the correct symmetry to form a linear combination together with any of the hydrogen orbitals in water. And so in that case, what will happen is that the B2 will remain completely static in energy, and will just become B2, and it will be a non-bonding orbital, as there's no way for it to have the correct symmetry with either of the waters. If we now start adding in electrons, so we can see that oxygen has 6 valence electrons, and then each one of these hydrogens has 1 electron, and we start filling in our MO diagram, what we will then see is that the B2 non-bonding orbital will actually be the highest occupied molecular orbital in our system, which is kind of what's expected, because we do think of water as having a lone pair that sticks out from it, and the way that you can think of it is that it's primarily the py orbital on that oxygen that contributes to that non-bonding highest occupied molecular orbital.